So this video addresses the superposition theorem. The superposition theorem applies when you have multiple sources. So you see I have in this case, a voltage source and a current source. So when you have multiple sources and you want to find a voltage or a current through a particular element, what superposition says is that what you can do is just pick one element at a time. So you see here I'm just or one supply at a time. So I've got this voltage supply here, and I can find the current due to just this voltage supply, and then find the voltage due to the second supply. In this case it's a current supply, but I'll find the current. In this case I'm finding the current through this resistor, but and I'm going to find first the current through this particular resistor due to this voltage source, and then the current through that same 6 ohm resistor, but I'm going to ignore the voltage source, or the first source, and look at the second source, which in this particular case is a current source. Right? So the rules is that you pick the source that you're going to do. Call it source A and source B. Okay, so here's my circuit for source A. So for source A, what I'm going to do is I'm going to short any other voltage sources. Now I don't have any other voltage sources, but all other voltage sources, I'm going to short all of those, and then I'm going to open all current sources. So I do have a current source, so you see this is now an open circuit here because there was a current source here, and I'm just going to open that up for now and find this current due to source A. So I'm going to find the current for source A, and then I'm going to find and then once I do that, then I'm going to look at my second source, which is source B. So I'm going to find my current for source B, and then when I'm done, my total current through that resistor will be the sum of the current for source A plus the current for source B. Alright, so we're going to find the current. You could find the current and the voltage. I mean, using Ohm's law, it's pretty much the same thing anyhow, right? If you find this current and you have the impedance, in this case the resistance, then Ohm's law is going to tell us that the voltage is, the total voltage would be the total current times the impedance, which for just that resistor would just be R in there. So that would be Ohm's law, and we can find that. So, but let me just review the rules one more time here. So the rules say start with a source, label them A, B, C, and for the first source, you go through, and any other voltage sources you may have, you're going to short them. Any other current sources, you're going to open those. So you short voltage sources, open current sources. You're going to find your voltage or current through your particular element or branch of a circuit, and then you're going to go through and do the next source. So if you have a second source, you're going to do the next source. So this is the source you're working on. You're going to short all voltage sources and open any other current sources. And then when you find all of those, you're going to simply add them. But now remember, this is AC circuits, so these are actually phasors here. So you're going to have some particular voltage with an angle, right, or a current with an angle. So you're going to have some current with some angle, and you're going to have another current with some other angle, which may not be zero. Okay, I don't know what it is yet, I haven't calculated it, but you're going to have phasors. So when you add them, you need to make sure you're adding them algebraically. You can't simply say A plus B, you have to include the phase shifts. So now the other thing I want to point out is that power, this does not apply to power, because remember that power is equal to voltage times current, okay? Or another way of writing that would be I squared times R for true power. This is P for true power in watts. And so you can't add power for source A and power for source B because of that squaring of the current. That's just not going to work. So what you need to do is you find your voltage or current, and then if you want to calculate power after you've found those. Okay, so we've cleaned up the drawing here a little bit. I'm just going to remove these rules now. We're going to go ahead and find the voltage and the current. So again, we have we have the current, or the supply, the supply A and the supply B. Alright, so this is for supply A, so that we're going to find the current IA, and this is supply B, so we're going to find the current IB due to the B source. And so the total current through, in this case, we're looking for the current through the resistor, which of course would also be the current through this capacitor. And so that total current through the resistor, call it ITR, is going to be IA R plus IBR. And so when we look at this circuit here, this one's pretty easy, because remember, we're going to open the current source and just find the current due to this voltage source. And so here now we just have a simple series circuit. So we just have a simple series circuit there. And so we can say that the current I, right, is, so I call that IR, I guess. Okay, so the current IAR is going to be simply my supply E1, and remember these are all phasors here, divided by the total impedance of this circuit, which is just these three in series. So that's going to be 20 amps, angle 0 volts, or excuse me, 20 volts, angle 0 degrees. Okay, 20 volts, angle 0 degrees. And then we have the, we're going to have a minus J6, or plus J6. I'm having a terrible time here tonight. Plus J6 for the inductor, X of L. We'll just kind of mark that. That's X of L. And then we're going to add to that just the 6, which is due to the resistance. And then we're going to subtract J8, which is X of C, the capacitor piece here. All right, and so of course that can simplify to 20 volts, angle 0 degrees, and then we have 6 minus J2, okay, and of course the units for this is impedance, so it's going to be ohms. So if we want to calculate that, then we pull out our handy dandy calculator, and I'm just going to use this octave program that I use most of the time. Actually, it's handy on if you're at a computer. And so I'm going to take my voltage source E1, and that's simply equal to 20, and then I'm going to have my Z total A. I'm going to call this A. I'm going to use lowercase, but I'm going to just call this A, which is going to be the 6 minus J times 2. Remember, you need to multiply. If you're using the software like this, you have to multiply J times the number. Okay. And so now we can calculate the current IAR is equal to E1 divided by ZTA. And so that gives us, now this is the rectangular form of that current. And so we can calculate the polar version or the phasor version of this. Which is going to be the absolute value of IAR. And then we have to calculate the angle of IAR. Now, this software gives the angle in radians, so I'm going to multiply it times 180 degrees and divide by pi radians to get the value in polar form. Okay. And so this is my value here in polar form. So it's going to be 3.16. Okay. So if I was going to put this in blackboard, it'd be 3.16 amperes. And 18.4 degrees, and that's a positive. Remember, the current is leading here, so it's going to be positive 18.4 degrees. All right, so that is my angle. And that is my current for the source A. Okay, so that is my current for the source A. Now really, I wrote this in blackboard form with just 3 significant digits, but when you're doing it, you should probably record at least 5 digits. Okay, so you should probably do at least 5 digits there. When you're doing your calculations, okay, to make sure that it's accurate. So I'll keep those 5 digits there for later reference. All right, so actually I've got 6 digits for the phase angle over here. All right, so now we're going to find the current due to the B source, which is actually a current source now. So actually, if we redraw this a little bit, what we have here is we have the current source, which is feeding the 6 ohm inductor, and it's feeding the resistance, which is in series with the cap. All right, so that's 6 ohms and a minus J 8 ohms for the cap. All right, so and there's a J with the inductor. All right, so now we have a parallel piece of circuit here. So we have a parallel piece of circuit. So when we're going to calculate the current, if we're going to calculate the current through this, we first have to either find the voltage, or we can use the current divider rule. So let me remind you of the current divider rule. So the current divider rule says that the current through the element, in this case my resistor, which is also the capacitor, but I'm only concerned with the resistor here, okay, but that is going to be equal to the total current times the total impedance divided by the impedance of just this branch. And so that is the current divider rule. Remember, the current divider rule is kind of the opposite of the voltage divider rule. And the current divider rule is really just doing Ohm's law twice. So we're doing Ohm's law the first time, which is the total current times the total impedance, which is giving us the voltage at this node, right? The voltage across this the node, and then we're going to divide by the impedance of that branch to find out that. So that's all we're going to do here. So, you know, if we wanted to, we could just say, let's just find the voltage, which again is just I total times Z total. So, but we first have to find Z total. So Z total, now this is a parallel, all right? So Z total, we're going to have a 1 over the J6 plus a 1 over the 6 minus J8. So that's going to give me the Z total for circuit B. Okay, so the Z total for circuit B here. And when you do this, make sure you use parentheses in your calculator. And so I'm just going to calculate that Z total here to start with. So I'm going to have a Z total B, okay, for due to my B source, and so that's going to be 1 divided by parentheses 1 over parentheses J times 6 plus 1 over parentheses 6 minus J times 8. Alright, and then I'm going to close that other parentheses. So notice here, right, I've got parentheses here, and then parentheses around there, and then my final set of parentheses. So you need to make sure that you have the parentheses correct. And so that is my total impedance. And notice it's actually a positive J this time. And so it's 5.4 and then 0, so it actually turns out even. And of course this is the rectangular form, but I like to write the impedances in rectangular form so that we can see you know, that this is an inductive term. So notice here, right, in this circuit the inductor has a smaller impedance. Remember, current follows the path of least resistance, and so this is just 6 ohms, where this is 6 ohms of resistance plus another 8 ohms of reactance, and so this is the path of least resistance, so it's actually going to have more current than what we would have in the branch that we're actually looking for the current in. Alright, but what that means then is that the inductor is actually dominant in this particular circuit with, now remember what we've done is we've shorted that voltage source there. Alright, so that's our total impedance. So we could calculate the voltage then at this node. Now this voltage we're calculating only applies for the current source. It's ignoring the voltage source at this point. But we could find the voltage VB, and that again is Ohm's law, so that's IT, the total current for source B, okay, the total current for source B, and times the total impedance for source B, which I guess I called TB right over here. Right, and so we have the current, which is 3 amps, angle 0, times the total impedance, which is this 5.4, plus 7 point plus J 7.8. Okay, remember it doesn't matter whether the J is in front or behind. Okay, and so then we can calculate that as, so that is going to be VB is equal to 3 times ZTB, and so that is my voltage. Okay, and again, that's the rectangular form, and I could convert that to polar form, but at this point I don't really need to, because what I need to find is the current through IR. And so again, so the current now through IR is this total voltage VB, right? And this is just Ohm's law, right? VB, so the total current for IB is the voltage VB divided by the impedance of this branch, and this impedance of this branch is 6 minus J8. Alright, and so we can calculate that. Alright, so now we're going to get IB is going to be the VB, which I have as my variable here, the 16.2 plus 23 in the rectangular form, and then parentheses 6 minus J times 8. And so this now is the current in the rectangular form, and if we wanted that current in polar form, okay, then we can just recall this equation and change the A's to B's. IB. I guess I didn't put the R's in there, so it's just, it wasn't very consistent there, so I just called it IB. Okay, and so that gives me that total current. Now, so this is the total current IB or IBR. Which is 2.846 amps at an angle of 108 degrees. Okay, so it's at an angle of 108 degrees. Okay, and so now we can come back up to our original, which I don't know if I can quite fit all on here, but so we come up here to the original circuit, and we're going to add these two together. Okay, so we're going to take our 3.1623 amperes at an angle of 18.43, and if you're just doing 5 digits, we could cut it off there, plus our 2.846 amperes at an angle of 108.43 degrees. Okay, so there's 5 digits there. And so now we can punch that into our calculator, and we can just add those two values together. So I'm going to have IA, which I called IAR. So I total is IAR plus IB, and it should have been IBR, but I didn't put the R on that one. And then if I want to get the polar version of that, I just need to change the B's to T's and get the polar version. And so this is my total, which is 4.25 at an angle of 60.4 degrees. Okay, so that is the polar form. And again, the units for that are amperes and degrees, and so if I was going to put that into Blackboard, it would be 4.25 amperes at an angle of 60.4 degrees. Okay, so that is superposition in AC circuits.